The topic of the video is the power of computational quantum fluid dynamics, CQFD, across various fields. For collaborations in this area, subscription, comments, and suggestions, people can contact me at the following email address, lix8666@gmail.com. Computational Quantum Fluid Dynamics, CQFD, is an emerging field that extends classical fluid dynamics principles into quantum domains, leveraging quantum mechanics and quantum-inspired computing for simulations and optimization. While still in development, CQFD holds potential applications in numerous industries, including engineering, healthcare, business management, manufacturing, aerodynamics, and beyond. 1. Engineering applications. CQFD can improve various engineering disciplines by enhancing computational models, optimizing fluid behavior at quantum scales, and integrating quantum-inspired machine learning. Thermal and energy engineering. Improved heat transfer models for cooling systems, microfluidics, and nuclear reactors. Structural engineering. Quantum material simulations for designing stronger, lighter, and heat-resistant construction materials. Fluid structure interaction, FSI, quantum turbulence modeling in wind resistance, bridges, and aircraft structures. 2. Healthcare and biomedical applications. Quantum fluid modeling can revolutionize medical diagnostics, drug delivery, and biological systems analysis. Blood flow and AMP, microfluidics. CQFD can model blood circulation, aiding in stroke prediction, artificial organ design, and cardiovascular disease analysis. Quantum nanomedicine. Targeted drug delivery using quantum-enhanced biofluid modeling for nanoparticles and medical nanorobots. Cryopreservation and AMP, organ transplants, simulating superfluid cryogenic conditions to preserve biological tissues for longer durations. Brain and AMP, neural dynamics, understanding cerebrospinal fluid, CSF, flow, improving neurological disease treatments. 3. Business management and AMP, decision science. CQFD, in combination with quantum computing and AI, can enhance predictive analytics, logistics, and financial modeling. Supply chain and AMP, logistics. Quantum fluid models can optimize transport networks, reducing costs and inefficiencies. Financial market simulations. Turbulence in stock market shares has similarities with quantum turbulence, allowing better risk assessment and financial forecasting. Customer behavior analysis. Quantum-inspired algorithms improve consumer trend modeling and AI-driven decision-making. 4. Manufacturing and Industry 4.0. CQFD can transform smart manufacturing through precision fluid modeling and quantum-enhanced production processes. Quantum material manufacturing, optimizing the production of nanocoatings, superconductors, and quantum materials. Process optimization, quantum fluid modeling for chemical plants, semiconductor fabrication, and additive manufacturing, 3D printing. Quantum-inspired robotics, enhancing robotic assembly lines and automation efficiency. 5. Aerodynamics and aerospace engineering. CQFD can revolutionize aircraft and space vehicle design through quantum turbulence modeling and hypersonic fluid dynamics. Hypersonic flow simulations, understanding shock waves and plasma interactions for hypersonic aircraft and re-entry vehicles. Quantum turbulence control, developing next-generation aircraft with reduced drag and improved lift-to-drag ratios. Rocket propulsion and AMP, spacecraft cooling, optimizing cryogenic fuels and plasma propulsion technologies. 6. Environmental and AMP, climate science. CQFD's predictive power can improve environmental modeling and sustainability efforts. Weather and AMP, climate predictions, modeling quantum turbulence and atmospheric dynamics to enhance long-term forecasting. Ocean and AMP, tsunami modeling, simulating fluid interactions in deep-sea currents, tides, and tsunami propagation. Carbon capture and AMP, air purification, designing efficient quantum fluid-based filtration systems for carbon sequestration. 7. Artificial intelligence in AMP. Quantum computing CQFD can merge with quantum AI, QAI, to solve complex fluid-related problems. Quantum neural networks for fluid dynamics, accelerating CFD simulations using quantum-enhanced machine learning. Quantum cloud computing, running large-scale fluid simulations faster and more efficiently than classical supercomputers. Digital twin in AMP, smart cities, real-time quantum simulations for traffic fluid dynamics, urban air pollution, and water management. 8. Energy and AMP, sustainable technology. Quantum fluid modeling is valuable for designing future renewable energy solutions and advanced nuclear systems. Fusion energy research, modeling plasma fluid dynamics in fusion reactors, e.g., tokamak simulations. Wind and AMP, hydro energy optimization, quantum turbulence modeling for efficient turbine and wave energy harvesting. Battery and AMP, hydrogen storage, simulating fluidic behavior in quantum-enhanced energy storage systems. Conclusion. Computational Quantum Fluid Dynamics, CQFD, has the potential to transform a wide range of industries by improving simulation accuracy, enhancing optimization processes, and introducing quantum-inspired computational techniques. As quantum computing advances, CQFD will become a critical tool in engineering, healthcare, business, aerospace, environmental science, AI, and energy sectors, pushing the boundaries of fluid dynamics and quantum technologies. Difference between computational quantum fluid dynamics, CQFD, and quantum computational fluid dynamics, QCFD. Though computational quantum fluid dynamics, CQFD, and quantum computational fluid dynamics, QCFD, might sound similar, they are distinct concepts with different foundations, implications, and applications. Below is a clear differentiation. 1. Computational quantum fluid dynamics, CQFD. CQFD refers to the computational study of quantum fluids, which exhibit behavior governed by quantum mechanics rather than classical fluid dynamics. It involves numerical simulations and models that describe the motion of quantum fluids such as Bose-Einstein condensates, BECs, superfluids, and plasmas. Key characteristics of CQFD. Studies quantum fluids that display non-classical properties such as superfluidity, quantist vortices, and zero viscosity. Uses quantum hydrodynamics, QHD, and Schrödinger-type equations to describe fluid motion. Governing equations include Gross-Pitesky equation, GPE, for Bose-Einstein condensates. Quantum Euler or Madelung equations for quantum turbulence. Relativistic quantum fluid equations for extreme astrophysical conditions. Applications of CQFD. Condensed matter physics, studying superfluid helium, superconductors, and nanofluidics. Astrophysics, understanding neutron stars, quark-gluon plasmas, and cosmic turbulence. Quantum computing and AMP, AI, modeling quantum fluid interactions in qubits and topological materials. Plasma physics, improving models for fusion reactors and ionized gas flow. CQFD focuses on understanding the dynamics of fluids that are fundamentally quantum in nature. 2. Quantum computational fluid dynamics, QCFD. QCFD, on the other hand, refers to the use of quantum computing to solve classical and quantum fluid dynamics problems more efficiently than classical computers. It leverages quantum algorithms and quantum hardware to perform simulations of fluid behavior, including classical turbulence and quantum turbulence. Key characteristics of QCFD. Uses quantum computers to solve Navier-Stokes equations, turbulence models, and quantum hydrodynamics faster than classical methods. Employs quantum machine learning, QML, and quantum Monte Carlo methods for fluid simulations. Can simulate both classical and quantum fluid dynamics, making it a more generalized computational approach. Uses quantum algorithms such as quantum lattice Boltzmann methods, QLBM, for fluid simulations. Variational quantum algorithms, VQA, for turbulence modeling. Quantum eigenvalue solvers for solving partial differential equations, PDEs, in CFD. Applications of QCFD. Aerodynamics and AMP, aerospace engineering, faster simulation of airflow, turbulence, and supersonic flows in aircraft and spacecraft. Climate and weather modeling, improved quantum simulations for hurricane predictions, ocean currents, and atmospheric turbulence. Biomedical engineering, enhanced blood flow simulations and drug transport modeling in biological systems. Manufacturing and AMP, industrial CFD, quantum enhanced fluid structure interaction simulations for designing efficient turbines, engines, and chemical reactors. QCFD is about using quantum computing to solve fluid dynamics problems, both classical and quantum, making it a computational method rather than a physical fluid behavior study. Key differences between CQFD and QCFD: plasma physics, quantum turbulence and AMP, vortex dynamics, astrophysical fluids, neutron stars, quark-gluon plasmas, aerodynamics and AMP, aerospace engineering, turbulence modeling in industries, weather prediction and AMP, ocean modeling, biomedical fluid dynamics, fire and combustion simulations, implications of CQFD versus QCFD. CQFD expands our understanding of quantum fluids, helping in advanced materials, superconductivity, and fundamental physics. QCFD revolutionizes computational methods for solving classical and quantum fluid problems much faster, with broad applications in engineering, business, climate science, and beyond. CQFD helps in studying exotic quantum fluid behaviors, while QCFD improves computational efficiency and performance. Conclusion: CQFD and QCFD are fundamentally different. CQFD focuses on modeling and studying quantum fluid behavior using classical computational methods. QCFD uses quantum computing to solve both classical and quantum fluid dynamic problems more efficiently. In the future, both fields may converge, where quantum computers, QCFD, will be used to simulate quantum fluids, CQFD, more efficiently, leading to breakthroughs in physics, engineering, and high-performance computing. If you enjoyed this discussion, don't forget to subscribe, like, and share. Stay tuned for more insights on AI, quantum computing, and emerging technologies shaping the future of software and humanity.